Okay, so let's go through some solutions to these practice problems. This is hopefully going to be helpful for preparing for the exam. We're starting off with a decode the machine code instruction into one or more assembly instructions. So you can see here this is a little longer than your average 32 bits, which means that we at least have, some amount of 16-bit instructions mixed with 32-bit instructions possibly. It is 48 bits long, so we definitely have at least one 16-bit instruction, so keep an eye out for that. And there may be, two more 16-bit instructions or a 16-bit and a 32-bit. So let's get started. So we're going to fetch 16 bits at a time. So I'm just going to translate this 01 or 11DF into binary, and we'll figure out if that is a 16-bit instruction or a 32-bit instruction. So 11DF is going to be 0001, 0001, 1101 for 13, and then 1111. And I'm just going to label these 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, so that we can easily refer to the format in the architecture reference manual here. So this is reference B from the website, and if you look at the notes, it'll tell you to go to page 108 to get started decoding an instruction. So the first thing we're going to do is look at the first 5 bytes as specified here. So if bits 15 through 11 take any of these values, it is a 32-bit instruction. So I'm looking at bits 15 to 11, these first 5 right here. So that's the first thing I'm checking. And I can see that it doesn't start with 111. So this is not a 32-bit instruction. That means it's a 16-bit instruction. And I'm going to click through on the C16-bit instruction encoding on page A5.5 to get to the 16-bit thumb instruction encoding. So we know that this is a 16-bit instruction. I don't have to worry about the next 32 bits yet, or getting the next 16 bits yet. So let's just decode this one and see what it is. So next, I'm looking at the opcode here. So that's the only thing listed in this format. That means that's the only thing I care about, and you can see in the table that's all that's listed here. So it's just opcode is going to tell us where to go next. So our opcode is going to be the first 6 bits here. 15, 14, 13, 12, 11, 10 is 6 bits. So I'm going to write down 000100 is my opcode. And now we just have to look through this listing of opcodes to see what matches. And in this case, the only thing that starts with 00 is the 00XXXX1. So it's going to be a shift, immediate, add, subtract, move, or compare on 5-6. So I'm going to click on that page. And this is going to bring me to the next thing that I have to decode. So now I'm looking at, I know those first 2 bits are 00, because that was sort of what was required from the previous pattern that we looked at. And so now I'm decoding the next 5 bits to see what is the specific opcode for this instruction. So I'm going to have another opcode here. They're named the same thing. I know it's a little confusing, but that's what they do. So the next 5 bits, 13 through 9, are going to be 01000. So again, I'm just looking in this table to see what does that match. And you can see here that 010XX is the only thing that starts with 010, and that's going to be an arithmetic shift right, so an ASR. So I can click on this, and that brings me to the ASR encoding. So at this point, I know it's a 16-bit instruction, and we're going to assume that this is the outside IT block format. So if you see 2 things there, you can assume the first one is the one that's going to work. We can see that the first 5 bits match what we have here. So 00010 matches this encoding. So now I have to find M5, RM, and RD, and that's going to tell me what this instruction is. So M5 is bits 10 through 6. So I'm just going to read those off. It's going to be 0, 0, 1, 1, 1. So bits 10 through 6 there. Then I have RM. RM is the next 3 bits. That's bits 5, 4, and 3. So 0, 1, 1. And then we have RD is the last 3 bits, which are 1, 1, 1. We can translate all of these to decimal. So 1 plus 2 plus 4 is 7. 1 plus 2 is 3. And 1 plus 2 plus 4 is 7. So those are all of the things that I'm going to put into this instruction. And then I'm just reading off this instruction encoding and substituting, filling in the blanks. So we have an ASRS, RD is R7, RM is R3, and the immediate starts with a pound sign or a hashtag, and that's 7. So that's our first instruction. We still have 32 bits to go, so we need to continue this. And next I'm going to look at EB77 to see what that is. So let's look at EB77, and that's going to be 1110. B is 1011, and then 7 is going to be 0111, 0111. Add an extra one there, sorry about that. So this is our next 16 bits that we're looking at. So again, I'm going to go back to my manual here. I'm going to go back to page 108 because that's going to tell me whether this is a 16-bit or a 32-bit instruction. So I look at the first 5 bits of this, and I can see now for this one, 11101 matches this bit pattern. So the 0B in front just says this is a binary number, just like 0x says it's hex. And then the 11101 says that this is the matching pattern. So this is a 32-bit instruction, meaning I'm going to need to look at all 32 bits here. And I'm going to go into the 32-bit thumb instruction encoding now. So I'm going to write out the rest of this because that means we are looking at the entire set of bits here. So I'm going to write this out over the top and go ahead and label them with 15 through 0. And then 15 through 0 so that it matches the format in the instruction manual that we're looking at. So this will be given to you on the exam, but it's good practice to do it in any case. So let's write out E is 1110, B is 1011, 7 is 0111, 7 is 0111. That's the first 16 bits. And then we have 0, which is just 4 zeros. We have a B again, 1011. We have a 0, 0000, and 5, 0101. And then, like I said, I'm going to label 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 15, 14, 13, 12, 8, 7, 6, 5, 4, 3, 2, 1, 0. So we have sort of two halves of the instruction, the two 16-bit values that comprise this whole instruction, and this lets us line it up very nicely with the format that's in the guide here. So I know my first 3 bits are going to be 111. I can sort of ignore those for the rest of the time. That's never going to be of use to me, so I'm just going to cross them out. And now I know op1 is bits 12 and 11, so that's going to be 0, 1 here. And now op2 is the next 7 bits, so that's going to be 0, 1, 1, 1, 0, 1, 1, 1. Or 0, 1, sorry, 0, 1, 1, 0, 1, 1, 1. So that's the next 7 bits here. And then op is going to be bit 15. In this case, that's going to be 0. So now I can look at my table and see what does this match. So we have 0, 1 as our op1. So that means it's one of these first 4 rows. Now I have to check to see what matches op2. And op2 is 0, 1, 1. So that matches only this 3rd row here. So data processing shifted register on page A5-26. Okay, so this gets us to our next set of encodings here. And now we have to look at the bits here to figure out what we have to do next. So let's look at what our new op is. Our new op is going to be 8765 of the first 16 bits. So let's see, that's 1, 0, 1, 1. And that actually gives us our answer right away this time. We don't have to look at RN or RD. If we look at what op is, The only thing that has 1011 here is subtract with carry, or SBC. So we know that this is going to be an SBC instruction. That's the only thing that matches op of 1011. So we can just click on that and move into the SBC encoding. So there are multiple encodings here, but of course we know that this is a 32-bit instruction, so it's not either of the 16-bit versions. We should match this up with the encoding T2, which is the 32-bit version of this encoding. So now, again, I'm just kind of pulling out the bits that I need from the bits that I was given to figure out what all of these fields are. So we can look at S is the 4th bit of the first part here. So bit 4 there is a 1, which means S is going to be 1. So this is an SBC S instruction. It is going to set the flags, and that's why that S is a 1. So we're going to add that S to the end. Rn is the next 4 bits, so that's 0, 1, 1, 1. That means Rn is 7 equals 0, 1, 1, 1. So I translated on the fly there. The next bit is 0. Then we have M3 is 14, 13, and 12. So M3 is 0, 0, 0, or 0. Though we're going to combine M3 with M2, so it's not necessarily just 0. RD is bits 11 through 8, so just reading here, it's nice that it's lined up for us. So it's 1, 0, 1, 1, which is 1 plus 2 plus 8 is 11. And then we have M2, which is the next 2 bits. Those are also 0, 0, so that's 0. So our immediate is going to be 0 for this instruction. We're not doing any amount of shifting here. Shifting would be what is encoded in that particular immediate if we were using the barrel shifter. Then we have type. Type is going to be equal to bits 5 and 4, which is 0, 0. And then the last thing we have is RM. So RM is the final 4 bits. That's 0, 1, 0, 1. That is R5. So now we can look at the SBC instruction here. We can sort of check to make sure that type isn't doing anything weird if we look at the rest of this, checking to see what that gets used for. It appears that it doesn't really show up here in the encoding, so it's just extra bits, I suppose, at this point. So now we can just encode this instruction, and it's going to come after the ASRS because it is after it in the chain here. So we're going to have SBCS. So this is just reading the encoding now. So SBC with the S, and then we're going to have RD, RN, and RM. So RD is R11. N is next is R7. Again, coming from here, and then RM is our final register, and that is going to be R5. And that's it. I know it's a bit of a slog, but that is how we would decode 2 instructions in a row here.